Hi, we can hear you fine.
Okay, you can hear me. You can see my screen.
Yeah, that looks good.
All right,
You might want to make it, I think, a little bit bigger based on feedback we've had
larger,
previously. Yeah, I think that's
better.
good. Yeah, that's great.
All right, so I start.
Yep, please.
Yeah. So because you said statistics and fitting, it's I think in the whole spectrum of this whole PyHEP conference, I guess I'm on the most theory-heavy side. So I'll be presenting on behalf of this SmodelS collaboration. You see that SmodelS is both a collaboration and a software tool. We use SmodelS for to talk about to refer to both the collaboration and the tool. And we're bothered with interpreting simplified models results from the LHC. So because I assume that the audience is more on the experimental side, the overall idea, I will be like going into the individual components later. The overall idea is that you have a fully specified theory, say a supersymmetric theory or a universal extra dimensional theory or something of the sorts. And our strategy is that we decompose these theories into their simplified models spectra, and then we match with a database that we built up of the simplified models results. So in the database, you will see later that we have roughly something of the order of 100 results, 100 publications from CMS and Atlas. So this will be the guiding principle, the silver lining, this plot. And I will go into the details, and like every detail can be attributed to one sort of position in this plot. So preparatory step, I think it should not be necessary because I wrote the requirements.txt file, but it also shows that SmodelS is in the Python index. So we understand ourselves as being fully embedded in the Python ecosystem, just like Zfit, the speaker before me. And this is something between a talk and a tutorial. So what you would need in order to run SmodelS, or what you would want probably, is a theory. And I provided one in the GitHub repository. The theory is specified in a format that we call the SLAJ format, Suzy-Lesouche accord format. In this case, I ran SLAJ plot by Andy Bugley over it, so you actually have an idea of what this theory looks like. You see it's a supersymmetric theory. It could have been something else, but it is supersymmetric. You see there's a bunch of Higgs bosons, something we call neutralinos and charginos, gluinos, colored SUSY particles, and all the sorts. So I will be discussing what SmodelS does with such a theory, with this theory as the example. So let me, again, because this is more of an experimental audience, let me briefly review what problem we're trying to address and solve. And the problem I kind of visualized with a few plots. The first plot is this one. This is actually an impression by Hitoshi Murayama. And it shows that the landscape of BSM theories that we try to test at the LHC is actually quite varied, right? You have supersymmetry, you have all sorts of extra dimensional models, you have superstring theories, and then composite Higgs, little Higgs, Higgs doublet models, dark photons, axions. You have a lot of theories, meaning sort of it's currently we're very uncertain about, on the theoretical side, where to proceed after the Higgs discovery. And all these theories and this landscape of theories, we want to confront with a very large number of experimental results, right? By now we have CMS just released their 1000th paper. So the question is, how do you systematically confront theories on a large scale? A lot of theories, and many of these theories, I should also mention, obviously have also a lot of free parameters. Supersymmetry, for example, the MSSM, which is maybe still our favorite model in some sense, it has more than 100 free parameters. And we have order of 1,000 publications. So how do we match this systematically? How do we start automating the model building? And when I say model building, I mean model building in the theoretical physics sense and not in the statistical sense, or actually in both senses. So let me briefly recap why we introduced simplified models around 10 years ago. That was around 2010, shortly before the Higgs discovery. We introduced simplified models in the experimental communities in CMS and Atlas. And the idea was that we wanted unphysical models that contextualize the searches for new physics. So a simplified model is an unphysical model. It has only a reduced set of BSM particles. BSM is beyond the standard model. In this case, for example, you only have two new particles. This one we will call the stop, this one we will call the neutralino, and the simplified model only introduces these particles. It fixes how these particles decay. And the production cross-section, on the other hand, is a free parameter in the simplified model world. In a supersymmetrical and a fully specified theory, the production cross-section will be fixed once you fix all the particle content and the decays and everything. In a simplified model, because it's meant only to describe, as a tool to describe the experimental findings, the production cross-section is a free parameter. And here we see the way we usually use these simplified models. This is one CMS publication, the result of a CMS publication. We see that here the simplified model is specified, and the actual information content that we, for the theorists, extract from this plot is actually the temperature plot, because the temperature plot tells me that if I have a theory that has a gluino-like particle with, say, 1500 GeV and an LSP-like particle with, say, 1000 GeV, then my model, the predicted cross-section, the cross-section that my model predicts, should be below cyan. Cyan is about 3 femtobarns, because if my predicted cross-section is above this value, my model is excluded by this result. This is how we use simplified models. And this is how we use them to contextualize experimental findings, so that actually the findings are expressed in a way that is very amenable to theoretical physics. Okay, that was the recap of simplified models. Now I go to the Python SmodelS tool that we developed. And you can think of the SmodelS tools as being composed of roughly 2 parts. And one part is this database of the experimental results that comes also with a language that we use to describe what we actually have, what these individual results constrain. And the second part will be the decompositor, the guy that decomposes a full theory. And then we match the two. So let me start with the database, and now I actually start with Python code. So you see we have a database object I import, and here I instantiate the database. The database can be local. You can write or augment a SmodelS database yourselves as a user, because it's a bunch of text files. We describe how to do this. Here we use the database. I prepared 2 databases. Unit test is in the default repository because it's faster. It's the database we use to do our unit testing of SmodelS. And here I'm running with the official database. So if you do this, it should already be downloaded. Why is it not downloaded? Okay, now it downloads it again. So what happens in the background is that if we use these default labels, the databases get downloaded from a CERN server. There is some repository at CERN, and we just fetch the pickle file that contains everything in binary format. So if we print this object, which is here, you actually see we're using SmodelS 1.2.3, and we have roughly something of the order of 100, the results of roughly 100 published searches in the database. Some at 8 TeV, some at 13 TeV. All right, So here you can actually, the database has this notion or this method called getExpResults, as in get experimental results. So here we have this line that actually queries how many results we have in a database. So there are all these different types of flags. I guess I can do this, right, with the question mark. Does that work? Yeah, so you see we can filter for the experimental results in all sorts of ways. But if you get the full database, it's roughly 100 results. We can also, we could also do this, get the analysis IDs for all the results in the database. Yeah, so this will give us a list of all the numbers of the analyses in our database, CMS and Atlas. So one experimental result corresponds to one publication of CMS or Atlas. And we think of one experimental result as very often being composed of several, what we call data sets, which corresponds to signal, usually corresponds to signal regions in the publications. So I don't know, Atlas or CMS SUSE 19006 doesn't just have one signal region. Obviously, it has, in that case, dozens to hundreds of signal regions. And we try to make the maximum use of the published results, obviously. So we try to have an as close as possible correlation. Like we try to have as much data as possible in our database. So here you could, in this line, what I prepared here is a question of how many of these signal regions do we have in a database, right? So we iterate through the experimental results in the database, and then we ask how many signal regions, data sets is for us a synonym for signal regions, are in each of these publications, and then we sum over this number. So we end up with something of the order of 300. And then as another sort of layer, we think of each signal region as being composed of several topologies. So topologies, if you think of this, each signal region can be populated by several of these simplified models. And we can have results in our database for the individual simplified models. So this is what we call TX names topologies. TX name because of historical legacy with CMS and our work within CMS. So you see we have something of the order of 2,000 individual maps in our database. And once you have this database of results, the next thing you would be interested in is seeing if you can construct likelihoods. Yeah, so you have your theory. Your theory predicts yields in the individual signal regions. You can construct likelihoods for this specific theoretical model. And here I show you how many. This is actually a very condensed line. So maybe I immediately go to this one. This is actually awkward code, but it's much more explicit. So here I go through these individual maps and I count for how many maps can I construct a likelihood. And the reason why we sometimes can construct likelihoods and sometimes cannot construct likelihoods lies in what data is published by these experimental collaborations. So if the experimental collaborations only publish observed upper limits, we cannot construct the likelihood for our theory. If they publish efficiency maps, number of observed events, number of background events, or if they publish an expected upper limit, we can construct approximate likelihoods. And because this is embedded in the phenomenological world, we are perfectly okay with approximate likelihoods. So here we go through the experimental results. We go through the signal regions in each experimental results. We go through the list of topologies, simplified models topologies in each signal region. And we count how many likelihoods do we have. And the answer will be that we have something of the order of 1700 for, like, we have something of the order of 2000 maps, and for 1774 we can construct approximate likelihoods. And then the question will be how to which of these likelihoods can we combine and which can we not, but this is something for the future. Now I wish to go from the database side to the decomposition side. So that's the second part of what makes up SmodelS, right? And the decomposition, I already said, the idea is you have a fully specified, your favorite supersymmetrical theory, and the decomposer is responsible for decomposing, exploding this into the individual simplified models topologies. And I show this also with code. We do a bit of a few import statements. The theory that we decompose is, again, is this PyHEP 2020 SLAJ that I prepared, some random supersymmetrical theory. I don't even know where I have the theory from. And now this is the line that does the magic, because this is the line that takes as input the theory in the form of an SLAJ file. There are some parameters that you can tweak and tune that I don't want to go into because they're very technical and very detailed. And the output is a list of topologies. And the list of topologies, I should make some, that there is one technical detail that I cannot spare you in this talk, unfortunately. And that is that we think of the graphs as topologies, and if we plug in for these line individual standard model particles, we think of them as elements. So topologies is sum of elements. So this would be the topology here, for example. This is what we will be looking at further down. And if I specify that this is an electron and this is also an electron, then I think of this as an element. This is a technical detail that only is supposed to make things more efficient in the decomposition. It's actually not something conceptually important, but sort of you're being exposed here to this detail. So I go through all the list of topologies. I can print them or I can describe them. And you see the topologies are mostly described by the number of decays. We always have 2 branches, and the number of particles that radiate, that emerge from each decay. More interesting is looking at individual elements because they're more physically interesting, more meaningful. So what I prepared here is that we look at the 4th topology here. The 4th topology is this type of a topology. So this topology is characterized by only 1 decay on one branch, only 1 decay on the other branch, and each decay radiating off only 1 standard model particle. So I look at all the elements that this topology is composed of, and you see that we always have 2 branches. This is our way of specifying these final states. And in each branch, sort of this element corresponds to a W that is radiated off on one branch of the theory and a W that is radiated off on the other branch. And what we see here is that each element specifies the masses of the BSM particles, but not the other quantum numbers. This is inherent in our SmodelS approach. So we say that these types, everything that looks like this and has a W being radiated off on one branch, W being radiated off on another branch, every theory like can be exposed to the same experimental results, which makes it possible that we apply, or that the mechanism automatically applies a supersymmetric, a search for supersymmetric theories to a universal extra dimension model, for example. And what we also have is what is called here the weights. And weight is actually a funny name, probably from an experimental point of view, because these are the theory predictions. So in this theory predicts that you have events with 2 W's in missing energy in the final states. And this is the predicted cross section for 8 TeV and this for 13 TeV for these types of events. So this is the decomposition of the theory, right? And the theory also predicts that, I don't know, that you have events with 2 Higgses being radiated off, and this will be the predicted cross section for these types of events. Okay, so on the one side, we have this database where we collect as exhaustively as possible all the experimental results. And on the other side, we have this mechanism to decompose a full theory into this simplified model spectrum. And now we connect these 2 parts. And I wish to say that we also, SmodelS ships with executables. So SmodelS, I think of SmodelS as a library, a module, a purely Pythonic or almost purely Pythonic library. But we also ship it with some standard executables, just as to make it easier for people who are not so into coding to actually make use of SmodelS. Remember, our target audience is actually more on the theory side than on the experimental side. But this, because this is a PyHEP conference, this does not merit too much attention. What is more interesting is that we can do this, of course, also in a module library type of way. So what we do here is, remember, we still have our theory decomposed into its simplified model spectrum. And this we kept in a variable that we called list of topologies that was here. So the decomposed theory is, this is just a Pythonic list of topologies, obviously. And we kept it in a variable called list of topologies. So we still have this variable list of topologies. And now what we do is we iterate through the database of experimental results. I capped it here just to make sure that the output does not sort of swamp your screens if you run this. So I only look at the first 10 results. But what I do here, or what we do here, is we confront the decomposed theory with the experimental results. And I think it's not worth going through all the details here. But if you run it, what you see is we have our theory, our SUSY theory. We expose it to the experimental results. We see that, for example, this Atlas SUSY 2015-06 result, which is a 13 TeV result, actually matched, can be applied to the theory. The theory predicts that some specific simplified model topologies are being produced with a production cross-section of this number here, 3 femtobarns, roughly 3.36. And the upper limit is 15 femtobarns. So the theory predicts about 3 femtobarns. The upper limit is the experimental. This is the experimental results, right? This is the theory prediction. This is the experimental result. So if the theory prediction were above the experimental result, we will consider the theory to be in contradiction with this specific analysis. In this case, what did I say? What numbers? In this case, the upper limit is higher, so the theory is not in contradiction with this result, and so on and so forth. Okay? So this is how we can actually make simple binary decisions. We can just throw away theories whenever there is a contradiction with an experimental result. But we also have likelihoods, so we can do smarter things, but this is not as, I don't want to talk about the statistical issues. Yes, yeah.
Well, I'll just let you know that you probably have about 4 or 5 minutes left, assuming that we started a little bit late.
Perfect.
So if you want, you have a few questions as well, I think.
Yeah, I need 1-2 more minutes and, or 2 more minutes. So perfect. Yeah, then I want to show one use case. And that use case is very often what we're interested in also to inform the experimentalists of what we think we have missing blind spots on as a community is we take a full theory, we decompose it, and we're interested in topologies, in simplified models that have large cross sections, but are nevertheless not excluded by any of the experimental results. And then the question will be for the experiment, why is that? Why are we blind to specific topologies? And this is one thing that SmodelS addresses with this missing topologies models. So we call this coverage. It's a model called coverage. We import it and we give it the list, the decomposed theory, and it will compute us all different kinds of topologies and simplified models that for one reason or another were not excluded by the experimental results. And then we may wonder, are they not excluded at all? Or do we just fall off this grid? So a few things that can happen is if we go up, where's the theory? Yes, if these maps, they're confined, right? There is a lower bound on the mass of the gluing and an upper bound. So we could miss a theory just because we fall out of these maps. So this is one type of diagnosis that we want to make, or just the maps not large enough. Another one is, do we have any result at all with this kind of a topology? So this is what you see here. You have some verbose statements about how much we're missing in general about this theory, how many of the channels, how much of the production cross-section. And here we make a statement about topologies that we miss completely. We don't even have any results in our database for this. And you see, for example, that, let's take this example here. We see that if you have a topology where only one jet is radiated off, and apart from that, only missing energy is being produced, we don't have anything in the database. And sometimes, often it's because our database sort of, that we should improve on the database. And sometimes we actually see that the experimental communities are as a matter of fact, blind to these topologies. So we wish to inform the experiments about these missing and blind spots. And this brings me to future developments. And the extensions we're currently working on is we wish to be able to describe all sorts of long-lived particles in exotic states, like displaced signatures, kinked tracks, disappearing tracks. This we cannot yet describe, but we will be able to describe in the upcoming release. For the likelihoods we have a working prototype that interfaces with PyHEP. So the PyHEP talk is actually, I think, comes today or something. And then we wish to study and understand which analyses are approximately uncorrelated and which aren't. And this is visualized here in this binary matrix. And in this binary matrix, for every pair of analyses that we have in our database, you can actually look up. If the box is green, it means that we assume that we can safely combine it. And if it's red, we assume, for example, if you have an Atlas razor analysis, which looks at just about every possible signal region and every possible final state. Obviously, we do not wish to combine this, trivially combine, like considering independent from another Atlas search. So we would not recommend combination. But the green ones, you can combine trivially just by multiplying the likelihoods. That's the idea here. Yeah, and here I give a list of links and references. Yeah, that would be all.
Thank you very much, Wolfgang. It's a very impressive set of tools, and it's great to see it was picked up in the chat and Zoom, but it's great to see a theorist and someone from the theory and pheno community joining this. I hope we can build this as we go forwards. I think we've got time for maybe one question. I think you've got the tab open. If you can switch over to the question tab on the top right of your screen.
Which question is
the question here is from,
yeah,
on Slido. Yeah, I think I can see it on the top right of your, not Slack, on Slido.
On Slido here.
top right of
How do
your
you
tabs.
do numerical normalization? Is that
the one that
for
I
me?
can see PyHEP 2020 sticking out. Or it doesn't matter. I'll read you the question and then you can answer that.
I think this is
Is
still
that-
for
How do you
I think it's still for set bit, right?
slide? That's right. That one of those two.
Was that the last?
The question
is that for
is.
me?
Here we go. Yes, perfect. I think I'm breaking up a bit, but that's right. How do you do numerical normalization for models with a large number of parameters?
I'm not sure I understand the question. Like models, there are so many words that we use differently in statistics and theoretical physics, right? Models is a theory model, a simplified model. Is that, I don't understand the question. I'm sorry.
I think the question was for set fit. It was already
Yeah,
there.
yeah, makes much more sense. Makes much more sense. So I don't.
My apologies. It must have came in slightly late. So then you have a question. You have a question from Eduardo. Since you're a theorist using Python, how did the points made in the keynote by David Straub on the first day? How did they resound with you? How did they echo?
How? Say again the question. How? If since you're a theorist, actually I'm not a theorist, but doesn't matter. I'm talking on behalf of theorists here.
So David made quite a few points about moving into Python and how it fitted well.
I'm sorry, I missed that talk. I cannot answer.
Okay. So maybe
Very
I can sort of summarize. How have you felt working in Python with SModels compared to other languages? How have you felt? I think
yes, I mean the productivity is like so much higher than C++, Fortran, anything before, right? I mean, like, so it speeds up development, I think, with respect to how we did things, I don't know, 10 years ago. It speeds development up by a factor of 5 to 10. We will actually, one aspect that I also want to see what you guys talked about, like number and so on and so forth. One aspect that we have is that the combinatorial part, right, where we decompose the theory into many individual elements and then we match. And this combinatorial part is actually becoming quite expensive, computationally expensive, because we want to be a very fast tool. We want to be a tool that you can run on 1 million points on a normal cluster fairly quickly. That is our asset. And we see that already with, in some cases, it takes 10 seconds or so to match a theory with our database. And that is because we pay the price. We have to have all the code is in, the combinatorial code is all in Python, contrary to, right? I mean, if you write a neural network, the actual code is in CUDA or something, but this combinatorial code is in Python. And so here we actually already pay quite a performance price because all the loops are in Python and they're not like vectorized or anything. So we really have to think a bit more. I already also looked a bit into NumPy and Cython and so on and so forth, but it's not yet completely clear to me how we tackle this.
Okay.
And another issue maybe is that maybe I should mention one thing, and that is that in the long run, we wish to make SModels differentiable so that you can actually add it in a chain rule and have a fairly long rule of differentiable code. So I'm obviously a big fan of differentiable programming too, just like everybody else, I guess, here. And so that one big vision will be that we have a gradient-based model inference in the long run. This is also something, and here Python is actually quite nice.
That's super exciting thinking in those terms. I guess there's two channels then, I think, on Slack. There's a topic, the performance, and topic reports differentiation. I think you probably get quite a lot of suggestions and help with some of these things. Yeah. Anyway, thank you once again, Wolfgang. I'm sorry that we're going to have to end it there. There's a handful more questions, so I'll copy those over to Slack after this.
Yeah, and I will actually... We take these offline, right? That's the idea. The questions we continue answering and everything.
That's right. So thank you once again to all